So I built a first-person shooter in COBOL. Yes, that COBOL, the language banks used in the 70s. And they still do nowadays. It started mostly as a random thought. I was wondering what the dumbest but still technically possible language would be for writing a small FPS-style game. And COBOL immediately stood out. It's old, verbose, missing most features even the shittiest modern languages have, doesn't even have a heap in the real sense of the word, and it's definitely not created for game development. So what better idea than to do a real-time raycast-based engine with all the features you'd expect in a video game. Now for a small reality check. In a modern engine, you get a ton of things for free. Windows, rendering APIs, math libraries, asset pipelines, input systems. You generally don't even think about them. COBOL gives you basically none of that. So instead of asking, how do I make a game? You end up with questions like, how do I get pixels onto the screen? How do I read binary files? How do I parse a map format? How do I even do vector math if half the math functions I expect don't exist? COBOL obviously doesn't have a graphics library, so my first idea was to just output an image file per frame. That worked, technically, but it was slow and clunky. Writing thousands of files just to simulate a screen refresh is not ideal. The game changer was treating the program as a frame generator. The COBOL program writes raw images to standard output, and another program displays them. So the pipeline looks like this. Each frame is just a ppm image, which is a ridiculously simple format. A ppm file looks like this. The code for writing pixels looks something like this. What's happening here is pretty straightforward. You first compute where the pixel lives inside the frame buffer, and then you write its RGB component. And once the program started piping frames to FFplay, I finally had a moving image. Now we're gaming. Quick interjection, if you find yourself enjoying this video, consider liking and subscribing. Once pixels were being printed, the next step was building the world itself. If you've ever looked into how early 90s games, like Wolfenstein 3D worked, you've probably seen this technique before. The idea is pretty simple. The world itself is actually 2D, it's just a grid of tiles, something like this. Each tile is either a wall marked as 1 or an empty space marked as 0. The player moves around this grid, but instead of looking down from above, the game renders a first-person view. That's where raycasting comes in. For every vertical column of pixels on the screen, the engine shoots a ray forward from the player's position. That ray travels through the world until it hits a wall tile. Once it does, the engine measures the distance between the player and the wall and uses that to decide how tall the wall slice should appear on screen. So pretty much if the wall is close, that slice is taller, and if the wall is further away, the slice gets shorter. And now you just repeat this for every column of pixels, and suddenly you have something that looks like a 3D hallway. This is what a basic implementation in COBOL would look like. And if you strip away the COBOL syntax, the logic is basically, first you compute the direction of the ray, then you move forward a little bit, and then check if we hit a wall. Finally, do that until we actually hit a wall. The algorithm itself isn't the difficult thing here. COBOL comes in clutch to make this competitive, however. In most modern languages, the array loop would maybe be like 10 lines long, and you'd probably use a vector type or a small math library. In this case, however, warm up your fingers, cause you're gonna have to get to typing every little util method you can possibly think of. And then, double that. You have to manually compute every intermediate value, storing everything in named variables, and use patterns that a modern language would compress into a single expression. It's what a more civilized programmer would call a bunch of anti-patterns. But now we have a world that renders correctly, so the next step is letting the player move around inside it. You keep count of their position and their angle. Movement just means adjusting those values. If the player presses forward, we move along the direction they're facing. But we can't just apply that move directly, because the player might walk into a wall. So the engine has to compute the candidate position first, check if that tile is empty, and only then commit the move. So now the code becomes something like this. What's happening here is that you first have to compute the next position, convert that position into a map tile, and check if that tile is empty. Another small complication is that COBOL doesn't encourage small helper functions the way modern languages do. So instead of writing something like is walkable, you end up repeating your checks inline in several places. But never mind that, we now have the player logic. But for the player to move, we actually have to get some input, right? Well, the display window is handled by FFplay, so it can't send input back to the game. That means input has to come from the terminal, so the game has to read keyboard inputs directly from standard input. But terminals normally buffer input until you press enter. For games, that's useless. What you have to do instead is have the program temporarily switch the terminal to raw mode, read characters one by one, and restore the terminal when exiting. It wasn't specifically hard to implement, at least conceptually, but as you know, theory and practice more often than not don't play nice. If you mess it up, you exit the game and suddenly your terminal stops echoing characters. That happened more than once. Well, now I can move around the world, so on to adding things that live in it. Enemies in this engine are basically just entities with a handful of properties, like position, health, speed, collision radius, current waypoint, and behavior state. At first, enemies were just static rectangles, and that was enough to test the projection math, but it obviously wasn't a game yet. The next step was giving them patrol paths. Each enemy has a list of waypoints it walks between. In the level config, it looks something like this. These values translate to this mapping. The movement logic is basically walk towards the current waypoint. Once the enemy reaches the waypoint, it switches to the next one. Now, in most modern languages, you'd probably have a vector library and do something like this. COBOL has none of that. Everything becomes explicit scalar math. Oh, and even basic functions like 8 and 2 simply aren't available, which forced me to write the AI logic to rely more on vector projections and distance checks instead of angle comparisons. Ironically though, this turned out to be the better choice as it's considerably more optimal for my case, but can't say I planned that. Once enemies started moving around, they also need to appear correctly in the 3D view. Walls are found by raycasting, enemies are drawn as sprites. A sprite is basically a billboard, a flat image that always faces the player. To render a sprite, the engine converts its world position into camera space. That tells us two important things: where it appears horizontally on the screen and how big it should be. Then, the sprite texture is drawn column by column, but only if it's closer than the wall behind it. That's where the Z buffer comes in. During the wall rendering pass, the engine stores the distance of the closest wall for every column on the screen. Later, when drawing sprites, it checks: is the sprite closer than the wall? If yes, draw it. If not, skip it. In code, the important check looks like this. Without this check, sprites would just overlap everything. Pickups, things like health packs or ammo, are actually implemented using the exact same system as enemies. Now, up until this point, everything, and I mean everything, map, enemies, pickups, were hard-coded. And that worked. Kinda. But it started getting rather annoying having to recompile the entire thing to load the new map. Also, it's sore on the eyes. Good programming practices and all that. So I made the engine switch to reading a level file, which looks something like this. Surprisingly, parsing this in COBOL turned out to be one of the hardest parts of the entire project. Instead of using individual variables for each token, the final implementation uses a token table. Then the line is split using unstring. That gives you something like this. This approach made the parser much cleaner than trying to manage dozens of individual variables. What was difficult was making sure the parser wouldn't corrupt memory if the level file had bad data. COBOL doesn't hold your hand, or foot, which you'll blow smooth off if you aren't careful. Which means a great deal of bound checks had to be added to keep things safe. And working, because it took me 3 different iterations to actually get past segmentation faults at startup. So we have the core functionalities, pretty much all the basic components of an FPS game loop. But it's still ugly, and we all know eye candy is the most important thing nowadays. Thus, time to bring textures and sprites into the game. Textures are stored as raw binary files. They're loaded directly into memory using system calls. Once loaded, rendering just means mapping wall coordinates to texture coordinates. Then, the RGB values are copied into the frame buffer. Sprites use the same texture format. The projection math converts world coordinates to screen coordinates. Then, each pixel of the sprite samples the texture. Transparency uses a simple color key, good old magenta. Most of you have probably tried at one point or another to make a Minecraft texture pack in your childhood adventures. And you probably remember all too well the background for the sprite sheets. This is exactly that. This makes irregular shapes possible without alpha blending. The weapon sprite is actually the simplest rendering feature. Unlike enemies, it doesn't exist in the world space. It's just drawn directly on top of the frame buffer after everything else. So here's the final look. Full game loop into play. and it even runs at a decent enough frame rate. It's actually bearable enough. You can get to fire your gun a few times, kill some enemies, get some pickups, and test out your map collisions. And remember, it's all COBOL. But as with every project that involves creating a game within an absurd medium, the question always floats in the back of your mind. Can you run, make, or play Doom with it? Well, how else can you know for sure if you don't give it a go? As a small piece of game history trivia, there is a reason, or more like a series of reasons, why Doom instantly overshadowed Wolfenstein 3D, even if it came just a year after. Which means that converting the current project would include stuff like DSP rendering. Doom didn't use raycasting, it used the binary space partitioning tree for fast rendering, which is a completely different rendering model. Variable height sectors. Current maps are flat. Doom had sectors with different floor and ceiling heights. And by tying sectors instead of having a single monolithic map layout, you got verticality, overlapping in your map areas, which is pretty much impossible in a basic raycaster. Dynamic lighting. Currently, the engine just darkens walls based on distance, whereas Doom has sector-based lighting levels. And better AI. Enemies would need more states and interactions. Right now you have patrol and chase. But if you've played Doom, you probably recall them doing a bit more than that. These are some serious changes, so because I still have some self-preservation instinct present, need to be smart about how I am going to approach them. A big decision I made at the very beginning was not to throw away the old system. I kept the original map path alive and added the new explicit sector-based path beside it. I had to make changes to the renderer too. Before, it mostly just drew one wall per ray, and that was enough. Now, it has to understand transitions between spaces. If you look for an opening into a taller room, it has to show the difference correctly. Where the opening is, which part is solid wall, which part is floor, and which part is ceiling. I also added shared geometry queries. These routines answer stuff like, which sector is this point in? What line do I hit first? And what opening exists between these two sectors? I reuse them everywhere, so line of sight, shooting, and movement all agree about the world. However, this step is still simpler than a full classic Doom renderer, so that I can have it plug and play into the current renderer, but you can't really tell the difference visually. Now, for the enemies. This is where I had to be a bit pragmatic. AI, even in the olden days, still meant quite a bit of logic to implement. A normal implementation is several degrees of magnitude larger in COBOL than in most other languages. So I just added a few more states, and improved their line of sight related movement. But besides that, I decided to keep them the same as before. Conceptually though, they are now treated differently in the world space. The same goes for pickups. Instead of being more like decorations on the 2D grid, they are actually interpreted as world objects. This also means I can have the player be aware of them across sectors. You probably didn't even think of this at first. I know I didn't, but sectors are technically separate world spaces. Navigating from one to another is equivalent to crossing through a portal which triggers the initialization of the newly entered sector. If the enemies would be, as previously happened, seen as part of the sector instead of individual objects, it meant that they, alongside pickups, wouldn't load until I, the player, stepped onto their respective sector for the first time. Now, could you call this a Doom clone in COBOL? Well, aside from the art, for which I concluded is best if I use copyright-free assets, and the much more rudimentary, well, everything, you could argue that it's not. Okay, jokes aside, it's technically a 2.5D Doom-like world, with Doom-inspired mechanics. But I think it's the closest anyone has ever gotten to implementing Doom from scratch in COBOL of all things. And I think that's an achievement in itself. However, if any unsuspecting victim, I mean ambitious programmer, decides they want to take it a step further and go by the book, I can only wish them good luck and easy rest for their wretched soul.